Chapter 8, slides 15 to 30. Okay, last mechanism of these two chapters, E2, or elimination second order. I'm going to go through the mechanism for this, and what I'm going to say is at the end of these slides, you're going to have seen E2, SN2, and what I'm going to tell you is that we will be able to distinguish when reactions are more likely to undergo E2 versus SN2. So versus. And then we also have now completed the SN1 and E1, and I'm going to keep those together because they are very indistinguishable. So we've got E2, which will be distinguished from SN2, which is distinguished from the SN1 E1 scenario. So ultimately, we have four mechanisms, but if I was really trying to go into the lab and choose SN1 only, I won't be able to do so. Okay, so I want you to keep that in mind. E2, unlike maybe the surprise that I unloaded on you when I was showing you E1, E2 is different than SN2. Okay, and you will be able to distinguish between them. Right off the bat here, what you'll notice is that I have your flashcard drawn out. This is the front of your flashcard, and the back is just simply going to say E2. Now, there are some similarities to SN2, but there will be some distinguishing factors. The first and foremost being that if I show you the mechanism, we're going to start with a tertiary alkyl halide. So this is an attribute very similar to SN1E1. But we're going to use something like T-butoxide. It's a T-butyl group on an oxygen, so it's bulky and it's strong. Bulky because of the T-butyl group, and strong because the oxygen is negatively charged. So this is also very, very different than SN2. SN2 preferred strong, but it didn't want the nucleophile to be bulky. So what we want to do is have strong, bulky, negatively charged systems so that we can promote the E2. Why? Because I don't want it to do SN2. Again, we have a leaving group. That's a similarity. The carbon that it's on is tertiary, so it's very sterically crowded. If I further sterically crowd my negative system, then I have a real tough time doing a nucleophilic substitution there, right? I'm not promoting SN2 by any means. I'm also not in the SN1E1 category either. So the best thing I can do, instead of the O- being a nucleophile, the O- is going to act as a base. It's going to find a much less sterically crowded hydrogen nearby to abstract. So it's going to turn to the carbons next door. Now, just like in the E1 scenario, I have three options here. Doesn't really matter in this case since all of them are CH3, so I'm just going to show you using one of them. This is a concerted mechanism, just like SN2. And the second bullet point down at the bottom is perhaps the newest construct for you guys. It's called anticoplanar, but it really isn't new. You guys have seen anti when we were doing Newman projections. This is when two groups on adjacent carbons are 180 degrees from one another. So when we were looking at the Newman projection, if we had a group A and a group B, and they were opposed to one another, right, 180 degrees, this was called anti. Notice that they're also in the same plane. So this is actually what is meant by anticoplanar. 180 degrees and in the same plane from one another. It's the same meaning. Sometimes certain books call it anti-periplanar, anti-coplanar. It's the same thing. It's just a fancy word for something you guys already know. It's the anti-Newman projection. So that's something we're going to come back to, but let's just focus on the mechanism. the oxygen minus is going to act like a base. And again, I wish I was ambidextrous and I could draw all of my arrows at the exact same time, because I can only draw one arrow at a time, these things look like a set of dominoes, but they're not reactive to one another. They literally are bond making and bond breaking all at the same time in a concerted fashion, right? It's not like, think about the word concert, right? The saxophone doesn't play and then the violin and then the harp and then the drum. They all play at the same time. I'm just not skilled enough with my pen to draw every arrow at the same time. So unfortunately, when I'm drawing the mechanism, it does kind of look like a domino effect. This happens, then this happens, then this happens. But understand, all of these bonds form and break at the same time. So as the oxygen grabs the hydrogen, the electrons between the carbon and the hydrogen fold in, and as that's happening, the electrons between the carbon and the leaving group break, and the bromine takes the electrons. So notice that there is no intermediate. It is one and done. And you end up forming your double bond. There's your new pi bond. All the arrows were drawn in one fell swoop. How does this relate to the rate? Well, very similar to SN2, it's a second order reaction, elimination second order. That means that both the concentration of the electrophile and the concentration of the base, in this case here, are important, raised to the order of 1. So when you add up those coefficients, they add to 2. So it's a second order. So if I increase the concentration of the base by 3, if I triple it, the rate will triple. If I increase the concentration of the electrophile by 2, the rate will double, right? And so we're going to see the same thing. This means, because you saw that there was just this one transition, right? The bond making and bond breaking happened all at the same time. There was no formation of a carbocation. This is, somewhat good news for us, because notice that there can't be carbocation rearrangements. They can't. You're never forming an intermediate. It's just boom, one and done. Starting material, product, whoop. Rate determining step, irrelevant. It's just one step, just a transition. A high energy transition, because all of these systems have to come close to each other, their electrons repel, but once they overcome the repelling electron clouds, they find that perfect bonding distance, and the reaction happens. How does this look, or how can we model this with our hands? Well, the way that we do it in ASL takes into account one of the more important aspects of the E2, which I'm going to talk about. And you'll see this reflected in the models with our hands. And that is the anti-coplanar, the anti-nature of the leaving group and the hydrogen. And we can actually model this with our hands. So what this means is that the leaving group and the hydrogen have to be anti to each other on those adjacent carbons. And since that's the only way that this one and done transition state can occur, things have to be lined up. It's like, getting ready before a race or a game. You have to have your positions, right? You can't just all be anywhere. All of the orbitals have to be aligned perfectly in this anticoplanar position, where the leaving group is 180 degrees from the adjacent carbon's hydrogen. That allows the orbitals to align so that this whole thing can happen in one fell swoop. If they're not lined up, this reaction can't go as planned. So that's why the anticoplanar nature of the E2 is represented using our hand models, to remind you that that is an important factor. Notice how it looks. So what's important with E2? Well, the electrophile, the alkyl halide, right? You'll notice that the trend is literally the opposite of SN2, but the same as SN1, but for different reasons. We favored tertiary for SN1 and E1. Why? Because you're forming a carbocation in those mechanisms, and it was all about the stability of the carbocation. But we're not forming a carbocation here. So if I want to do E2, why is tertiary favored? Tertiary's favored is because we want to have as much, we want the steric hindrance so that it doesn't compete with SN2. The trend observed is due to avoiding SN2 competition by blocking reactivity at the carbon using steric hindrance. So if I have a bulky system around the leaving group, then I'm kind of shielding the carbon with the bromine from being attacked as with the nucleophile. Because again, the difference between a base and a nucleophile, it's like O- versus O-, they're the same. So how do I direct that O- to do what I want it to do? Well, I kind of shield or block using steric hindrance the carbon with the bromine so that it has to go for one of those outskirts, puny little hydrogens that are much easier to pluck off. I'm sort of forcing it to go elsewhere. The leaving group trend, no surprise here. Once again, iodine is better than bromine, is better than chlorine, right? It's better than fluorine. Iodine, I mean, the leaving group is a leaving group is a leaving group. That's what the whole point of these two chapters are. Alkyl halides are great leaving groups. That's why they're all put together in these two chapters to discuss the chemistry we can do with them. I'd say that's the stable, unchanging variable, right? It's not a variable, it's our independent. It's consistent through these two chapters. What about the base? Well, the base needs to be strong, right? So we want the base / nucleophile to be strong. So, negative charges are great. We also, if I can, I prefer to make it bulky. So you might not have to worry about it being super, super bulky if you already have a tertiary system, because you're using the tertiary nature of the alkyl halide to block. But let's say you had a secondary bromide. Oh, remember those pesky secondaries? They can go either way, they're kind of in the middle, so they're not easy to decipher what mechanism to employ. So if you have a secondary, I mean, it's blocking a little bit, but if you really want to ensure E2, then bulk up your base. Make the base bulky so that it's even harder to get in there and do a nucleophilic substitution. It's more likely to go after one of the hydrogens at the carbon next door, right, if it's big and bulky. So secondaries can undergo E2, but you might have to increase the bulk of your nucleophile even more. So you want it to be bulky. You really just want to avoid doing an SN2 because they can compete, but I just want to show you that you have control. And because it's a second order reaction, the nucleophile does play a role in that step. And so you can change things up. The concentration of that base, I should say base, not nucleophile, the base is also part of the equation. So write it in, right? So because we're starting and ending and only having a transition state, the concentration of the base can be increased to get this rate to go faster. So I just want to make sure that you're recognizing that both are in play at the exact same time. Also, when it comes to solvents, we're going to see the same thing as SN2. If we have a strong nucleophile / base, they're going to be negative species, okay? So you might have an O-, like maybe you had T-butoxide, right? It's purchased as a salt. We don't buy O- off the shelf. We buy the salt, and its counter ion might be potassium, might be lithium. And it really helps free up that O- to do its job. If you can entice the potassium away, cage it up, if you will, using a solvent like the crown ethers that I mentioned in SN2, or just a polar aprotic system like DMSO, acetone, something like that, something that's not protic, but because, again, a protic system would just entice the T-butoxide to do acid-base chemistry with it. You don't want to compete with your solvent. So you don't want to use water to say, hey, come grab one of these hydrogens. No, the O- has got to react with your organic molecule, not the solvent. So don't give it something acidic to work with. So stay away from those protic solvents. Acetone doesn't have an acidic proton on it, neither does DMSO or DMF. So stick with an aprotic solvent. Still has to be polar enough, though, to dissolve everything, just not enticing enough to have a proton that could act as an acid. Okay, let's get back to regioselectivity and stereoselectivity. We're actually faced with a similar dilemma as we were in E1. If I have this bromine as shown, I have the potential, because of its position, to deprotonate at either of the carbons, left or right of it. And due to rotation around those single bonds, I know through a Newman projection, I will certainly be able to align a bromine anti to either one of the hydrogens, left or right. You know, you've got to consider that. If you can't orient and twist the molecule to put the bromine and a neighboring hydrogen anti-coplanar in the anti position, then you can't ever set it up for an E2. That might be, something that stops you from doing E2. So I can do it in both of these cases. So all of these A, B, and C products are possible. And I'm showing you the actual experimental distribution of them. The major product, again, would have taken the proton in order to give the more substituted double bond. So A and B lead to the more substituted double bond, right? Because they're both di-substituted. Removing the hydrogen on the end leads to C, a monosubstituted. So first and foremost, from a regioselectivity issue, right, we're seeing a difference in regioselectivity due to Zaitsev's rule. The stability of the pi bond. Okay, so I have rationalized why I'd rather go after that middle hydrogen to lead to a di-substituted double bond versus the proton at the end leading to a monosubstituted double bond. According to Zaitsev's rule, this helps me solve my regioselectivity issue. Which isomer am I going to get if among the 72% A plus B mixture, which one do you think is the major isomer? If you said A, right, A is favored. The reason being is that B is the cis conformer, or I should say stereoisomer, and A and B are diastereomers. And B has some steric hindrance in the cis geometry. Therefore, A is more stable right, because it's trans, due to having less steric hindrance. Okay, so I know that A and B are both going to be more populated than C, but the major product for this system is going to be A. A larger part of the 72% will be A. Okay. I also want to do a little note to you guys that sometimes it looks like you have a tie. And among some of those ties, not always, but sometimes you can actually see other things other than Zaitsev's rule at play. Let me give you an example. Here we have an alkyl halide. You're like, wait, there's my leaving group. And I am going to do an elimination. I have an OH minus, and I could have given you T-butoxide to say, all right, we're going to do an elimination. You have two choices. You have the carbon next door on the left or the carbon next door on the right. And if you really looked at it, you'd say, well, I'm going to form a di-substituted system either way. If I remove a hydrogen on the left versus a hydrogen on the right, if I remove A versus B, right? The O minus grabs B, folds in, kicks out, all at the same time. Here are the possible products. The cis and trans version of removal of B, the cis and trans version of the removal of A. There are 4 possible products. Now, the difference between the first 2 at the top and the bottom 2 are constitutional. These are, A versus B proton is a regioselectivity issue. Which region are you going to pull from? I'm going to let you know that, first of all, let's eliminate 2 of these. Let's take away the cis double bonds, right? Because both of these are cis alkenes, while the second 2 on the left are trans alkenes. As I drew cis again. There we go. So we're going to eliminate the cis because we know that cis is higher in energy than trans due to steric hindrance. So why is the removal of A better than the removal of HB? And the key here lies in conjugation. The pi bond system, because of resonance, they're talking to each other. These 2 pi systems are conjugated, right? Pi system next to a pi system. This allows for resonance stability. Notice the isolated pi bonds. They're separated by that sp3 carbon in the middle. They can't resonate. They can't talk to each other. So that's much less stable. So due to conjugation or resonance, conjugation just means pi bonds can talk. It's the same as resonance, right? These electrons can move freely across a larger area of atoms, number of atoms. This is going to be the major product. So despite having a secondary versus a secondary, the pi bond next door helps to form a more stable product, leading to one major product. We could do the same thing for the bottom case. Here's the alkyl bromide. That is my leaving group. I have to consider the 2 hydrogens at carbons next door. There's hydrogen A and hydrogen B. And if I remove either one, let's just not even think about the cis. Let's try to go for the gold. I would form this or this. And if you'll notice, the pi system of the benzene ring is conjugated to the double bond had I chosen to remove HA, versus the benzene ring, which is conjugated with itself, is not talking to the pi system that when I remove the HB, because it's got that wall between it. It's got that sp3 tetrahedral carbon breaking conjugation here. The sp3 carbon at that point just stops the two pi systems from talking because they can't work through each other through resonance. So the major product for this, despite both hydrogens A and B being on secondary systems, you do see a difference in the product distribution. So Zaitsev's rule, at first it was, the more substituted, the better. But what we really want to do is consider the most stable pi bond, right? So given all of your options, find the pi bond that is the most stable. You want to look at substitution patterns, but you also want to look at resonance or conjugation. Okay, let's spend a little time talking about this anti-coplanarity, or anti-periplanar as some books call it. I don't really mind. It just means anti. We need the hydrogen, that we're going to take off. So let's put regiochemistry aside. Let's just concentrate on this anti-coplanar thing. The hydrogen that I remove has to be anti to the leaving group. Okay, so I've color-coded these. So as drawn, like if you were to turn the molecule as drawn into its Newman projection, as drawn, you can see, even from the side view, that the hydrogen and the leaving group are on the same side. They're both up. So the Newman projection reflects that. What we need to do is we need to rotate around the single bond, and it doesn't matter which way you do it. You'll notice that this is what you get. The hydrogen and the leaving group are now, because of rotation, anti to one another. And when I look at that in my Newman projection, I can see this, right? Because this Newman projection here is looking down that carbon-carbon bond, and it's got the hydrogen going straight up, and in the back, it's got the leaving group going straight down. And this is what helps us, because when we have our base, our OH minus or whatever it is, grabbing the hydrogen, the electrons are all in line orbitally to do this flow. Everyone is set and ready to go. In order for an E2 reaction to occur, you are required to have the hydrogen and the leaving group on those adjacent carbons anti to one another. If you cannot get them into that situation, E2 will not work. So let's revisit this last example we did on the previous slide, the one that gives us cis and trans. Another reason for why trans in this scenario, it's still a steric hindrance, but you can see it a little bit more here. When you consider the two hydrogens next door, okay, A and B, let's do a Newman projection, okay? So here we're gonna look at a Newman projection. We're gonna stare down the barrel of that carbon. And what they've done is they've put the bromine, they've already twisted things for you. So the bromine is in blue, okay? And what you're seeing is HA and HB. Okay, they're highlighting HA for you. Now, because of the wedge and hashes that they've outlined, they're showing you that there is a difference between HA, the HA forward and the HB backwards. If you're tagging them, if you could decipher between them, you would see that one of them, when you're looking at the Newman projection, places these ethyl, the ethyl and the methyl, right? The ethyl in the back and the methyl in the front. Notice that when you're plucking off one of those hydrogens, those two groups are oriented also anti to one another. Now, take this HB and just rotate the back so that HB is now anti-coplanar to the bromine. That's what they're showing in this model. And in doing that, the whole back carbon rotates. So the CH2 moves over, the HB moves to the anti-coplanar position, right? And everything moves along with it. And so what you find now, if you keep the front the same, HB is now ready to be plucked off. But look what it does to the R groups. They're steric hindrance now. Those are gauche to one another. That's not good. Therefore, putting the HA of those two, the one labeled HA is the preferable one because it puts the two R groups opposite to each other. This is what leads to the trans double bond. It's not happening. This is what I want to show you, is that the molecule, when it's undergoing this reaction, it doesn't know what the product is going to be. Okay? Molecules are not, future tellers, right? They're not like, oh, I know that if I do this, I'll get to that. They're not smart like that. Everything that's happening in this reaction is happening in the transition state. It's happening in the setup. Okay, this is your transition state setup, the anticoplanar setup. Things are getting set up in the best feeling way, right? That's all happening before. That's always happening before. It's not, oh, I get to choose, right? In this case, I have two hydrogens, so I got to choose the one that would put those two groups opposed to one another. But what I want to tell you is that because anticoplanarity is required for this reaction to work, sometimes the best Newman projection that you can get might give you cis. Why? Maybe there's only one hydrogen next door and you had no choice but to put them anticoplanar and you ended up getting a cis double bond. It is what it is. You have to set up the reaction. If you have a choice, then by all means, try to lower the energy of that transition state to get everything as far away from each other as possible. But what I'm telling you right now is sometimes that's just not possible. You get what you get. Okay, here's an example. The E2 reaction may also produce a major product that might be surprising. All right, let's do this step by step with one another. Okay, we've got this leaving group, the chlorine. I'm going to tell you we're going to do an E2. Okay, so I'm going to make this easy on you. Here's the carbon. There's my leaving group. This is my base. Start, organizing your thoughts here. It's a strong base. I have a tertiary chloride anyway, so I probably would have decided this was an E2 system to begin with. So no surprise here. That is a negative, strong negative base, and I've got a tertiary leaving group. Okay, now I'm going to look at the two carbons next door. Each of those carbons, one of them would lead to from a regioselectivity standpoint, one of them would lead to a more substituted double bond. Now, understand that if we put a double bond between the two carbons indicated, the yellow and the blue, if I removed HA, I would actually form a tetrasubstituted double bond. As opposed to pulling off one of the HBs, I would form a tri-substituted double bond. So I'm going to go for the gold. I'm going to go for the regioselectivity that's going to give me a more substituted double bond. Okay? All right, so I'm going to choose HA because it leads to a more substituted double bond. This is the regioselectivity issue. Okay, so this is regioselectivity. I also need to consider stereoselectivity. Okay, notice that the HA is forward and the Cl is forward. They're both forward. I could do this two different ways. I could draw a Newman projection, or I could try rotating one of them so that the HA was in the back. So I need to rotate these. I need to get this set for anticoplanar. So what I'm going to do is I'm going to keep the chlorine. Well, you know what? I like to somewhat twist this like this. Like our hands in ASL. I want to make the hydrogen A and the chlorine, I want them to be anticoplanar, and I want to put them in the plane of the paper. Let's figure out what that means for the other groups off of the chlorine. If I push the chlorine into the plane of the paper, then out pops the ethyl, and the methyl kind of kinks up. So I'm literally, you gotta look at it. Think Newman projection and look down that bond. I'm twisting it so that the chlorine is at the bottom, the ethyl pops to my left and out, and the methyl is to my right. You might have to make a model of this with your modeling kit. If I want the hydrogen in the back, on the back carbon, what's going to be down and wedged and down and hashed? Well, again, I have to, with my mind's eye, just kind of rotate it just a bit. And when I rotate it just a bit, so that that hydrogen is still up, but just move to the left so that it's straight up and down with the chlorine, what I also notice is that the ethyl pops out of the page and the methyl stays back. I now have anticoplanar alignment. This is anticoplanar. I am now ready to use my base, take off the HA, cascade, cascade, all at the same time. And here is the double bond, the carbon-carbon double bond that I make. Notice the relationship between the ethyls. They're both in the front. And those methyls are both in the back. Technically, this is a cis double bond. Both ethyls, the bigger group, are on the same side, causing more steric hindrance. But you know what? I had no choice. Due to the stereo centers that were given to me, this was the only possible way. There was only one hydrogen. Only one hydrogen. Had there been two hydrogens and not a stereo center at that position, it wouldn't have mattered. I would have been able to twist it to get all of those bigger groups away from each other. But be careful when you have only one hydrogen and it's part of a stereo center. Why? Because you are at the mercy of anticoplanarity. You have to align that one hydrogen with your leaving group, and you get what you get. This is the major product. You're actually never going to be able to form the trans product. You also want to be careful when you're looking at cyclohexanes. Cyclohexanes also have to have the leaving group and the hydrogen anticoplanar. And the only way that you can do that is for them to be axial up, axial down next to each other. Let's look at some examples. If I had this molecule with a chlorine off of it and I wanted to undergo an E2, okay, I'm just telling you, do an E2 on this. All right, well, I'm going to redraw it down here, and you'll see that the chlorine, as it is right now, is in an equatorial position. What I'm saying is that we need to get it into the axial position in order to consider right, this is the carbon here, this is the carbon here. Down is down. It's just down axial. Now it's actually in a position where the next door neighbors who have hydrogens in the axial position, right? Now it's aligned. You can get this, you can see this anticoplanarity really nicely. What's anticoplanar with the chlorine when it's in the equatorial position? One of the other carbons of the cyclohexane ring. So you just have to flip the chair to get it into the axial position in order for the reaction to go. How does this affect when you have substituents next door? Well, again, notice that my chlorine is in the equatorial position. So I'm going to just redraw this because I like to draw in the hydrogens in these positions. So here's my chlorine, here's my carbon, okay? So I need to consider the carbons next door. But I can't get the chlorine in an anticoplanar right now. So I'm going to consider the flip. Here's my chlorine. It's now axial up, which is good. The carbons next door are left and right. And I want you to notice that the only hydrogen that is anticoplanar is the one on the left. Notice that the methyl group is taking up residency at the axial position anti to the chlorine on the other side. So there's no possibility that I could form the double bond in that direction, even though that would be the direction that would give me the more substituted double bond according to Zaitsev's rule. That's not the one I can go after because there's no way I can orient it such that both the chlorine and the nearby hydrogen are anti to one another. So I'm forced to go after this hydrogen. Okay, double bond is here, methyl is here. I want you to understand what this looks like in a 2D. I'm going to do the same exact thing as above. Notice that the methyl group is down and the chlorine is up. What does this look like in a 2D? The methyl group is down, back, right? And the chlorine was up. Now, if I was doing this E2 with a base here, you might even see it. I'm showing you using cyclohexanes why you can't get anticoplanarity, because you can see it very easily with the axial up, axial down. In a 2D way, this is the same problem. In a 2D way, maybe you're like, yeah, I prefer not to draw the chairs. Put in the hydrogens, right? Put in those hydrogens in the next door positions. You've got chlorine up. The only way I can eliminate a hydrogen that's back, notice that this is the only H down. The other hydrogen on the other side, you can't get at because they're both cis to each other. You can't change the stereochemistry. It is what it is. So therefore, the OH minus, I'm doing the same exact chemistry as I did above, is only going to give you one major product for this reaction due to the restraints or constraints of anticoplanarity. That is the only double bond you can get. What would you get if I had told you, don't do E2, do E1 on this reaction? What would the major product or product distributions be? Here's some more practice with E2. So in these, I want you to do E2 for every single one. I'm just telling you. You don't have to worry about figuring out which mechanism do I have to use. No worries, just do E2 on all of these to give you some practice. Notice that you're going to have to consider anticoplanarity to figure out your major product.